Hello.
Hello.
Yeah. Can you guys hear me?
Yes.
Yeah.
Okay. So today we'll start discussing about divisors. Before we do that, I want to talk about one type of function that will be important. So we'll talk about arithmetic functions and one particular type of arithmetic functions, which are called multiplicative functions. So first of all, what is an arithmetic function? Everyone knows what a function is, right?
Yeah.
Yeah.
Basically, it's a rule connecting one independent variable to a dependent variable, right? Or a set of ordered pairs.
Yeah.
So, what is an arithmetic function? It's a complex valued function defined on positive integers. So, what that means is the output of the function could be a complex number, doesn't have to be real. Okay.
Hmm.
So, and what is the input? The domain of it is positive integers. So it is defined like this, Z plus to C. Does everyone understand what is Z plus?
Yeah.
It
Yeah.
is the set of positive integers. This is the domain. Okay.
Hmm. Okay.
And the output or the codomain here is complex numbers. Now, there is a reason why we are talking about all this. So, this is a general arithmetic function. Inputs will be positive integers, output will be some complex number, right? So the specific type of arithmetic function that we want to discuss is multiplicative functions.
Okay.
What are multiplicative functions? What that means is f of mn should be equal to f of m times f of n. For all positive integers m and n. Okay. And here the m and n, GCD of m and n should be 1. So
Oh.
basically, anytime you have an mn as an input to a multiplicative function where m and n are co-prime, relatively prime to each other, the output will be the f of m times f of n,
Yeah.
right? So this
Yeah.
is a normal property that happens quite a lot in number theory. Because if it is multiplicative function, then you can represent f of any number n as f of the prime 1 to the power alpha 1 into f of prime 2 to the power alpha 2, because n has a prime factorization of p1 alpha 1, p2 alpha 2, and so on. What do I mean by
Uh,
that? Any n can be prime factorized like this, right?
Yeah.
And you know that p1 and p2 are co-prime to each other, right? So if you
Yeah.
want to find something about a number f of n, you can calculate that by doing the individual prime numbers powers f of that and product of those. Correct?
Yeah.
The reason is that this function is multiplicative, so this result will be true, and this happens quite a lot. That's why we are talking about it right now. Okay. So also, if a function is multiplicative, then f of 1 will be equal to 1. 1 is
Oh.
an input integer, f of 1 will be equal to 1. The reason is because, why is this happening? Because whenever you do f of a, and suppose f of a is not equal to 0, then you can write it as f of a into 1. And because it is multiplicated, it will become like this, right?
Yeah.
And if f of a is not equal to 0, this equality is true only if f of 1 is 1. Correct?
Yeah.
So for any multiplicative
Yeah.
function, as long as f of a is not equal to 0, f of 1 will always be equal to 1. Because of the property, this property, where m and n are co-prime. Do you understand?
Yeah.
Yeah.
So we will see examples of such function, but the main property that we'll be using is any number can be written in terms of prime factors like this. And if I need f of n, I can calculate that by doing this now. That is the typical application that you will see. So many important functions on positive integers are multiplicative. We will see some examples. Now we start with our discussion of divisors. All of this was introduction only because sometimes in functions on divisors, you will need this result. Okay. So first definition that I want to discuss is for a positive integer n, let d of n be the number of positive integer divisors of n. Integer divisors of n. So we can write this d of n like this. D of n is equal to sum over 1 wherever d divides n. What does this symbol mean? So you keep adding 1 for all numbers such that d divides n, right? So for
Yeah.
example, if I have to calculate d of 12, so sum of d divides 12, you keep adding 1. So what happens? When you check 1 divides 12, so 1 comes for d is equal to 1, plus 2 divides 12. So again 1 comes for that, right?
Yeah.
And then 3 also divides 12, so 1 for that. 4 also divides 12, 6 also divides 12, and finally 12 also divides 12. Correct?
Yeah.
Yes.
So this summation will give us 6 now, right?
Yes.
So we have come up with a way to write this d of n. You don't have to say it in words all the time. D of n is the number of positive integer divisors of n. But the way to write it is summation of 1. And when does the summation happen? Whenever d divides n.
Hmm.
Right?
Yeah.
This sum runs over all the divisors d of n. Correct?
Yeah.
Yes.
So that is the first definition. This is the first arithmetic function that we have. Okay. Now the second definition, definition 2, is for a positive integer n. We will let sigma n be the sum of positive integer divisors of n. Positive integer divisors of n. So we want to add up all the divisors. So now how should I represent this in an analytical form? Just like here, I wrote d of n, right? How should
Yeah.
I write sigma of n?
The sum of D.
Whenever d divides n.
Yeah.
So this will give us the sum of all the divisors, right?
Yeah.
This was just giving us number of divisors. And this gives us sum of divisors. I hope it is clear what is happening.
Yeah.
Okay. Now, let's try to derive some formulas. So both of these functions, d and sigma, are multiplicative. Both D of n and sigma of n are multiplicative. So what that means is D of mn will be D of m times D of n as long as m and n are co-prime to each other, right?
Yeah.
So from there, you can easily show that D of n can be written as alpha 1 plus 1, alpha 2 plus 1, and so on till alpha k plus 1, where n was equal to p1 to the power alpha 1, p2 to the power alpha 2, till pk to the power alpha k.
Yeah.
This is the prime factorization
Yeah.
of a number, and D of n comes out to be this. Because when you do D of n here, you will have to do D of p1 to the power alpha 1 into D of p2 to the power alpha 2 and so on, right?
Yeah.
And you can try to count what are the divisors of p1 to the power alpha 1. So obviously you will start with 1 and you will start with p1 squared till p1 to the power alpha 1, right?
Yeah.
All of these are
Yeah.
divisors of this number. So you can clearly see that this is alpha plus 1 divisors.
Oh, yeah.
Correct?
Yeah.
And because it is multiplicative, we multiply every one of them and we get this answer for D of n, right?
Yeah.
I hope you are understanding.
Yeah.
And similarly, you can prove that sigma of n will be equal to p1 to the power alpha 1 plus 1 minus 1 by p1 minus 1, p2 to the power alpha 2 plus 1 minus 1 by p2 minus 1, and so on till pk to the power alpha k plus 1 minus 1 by pk minus 1, right?
Oh, yeah.
Why? Because this function is also multiplicative. So you have to do actually sigma of p1 to the power alpha 1 multiplied by sigma of p2 to the power alpha 2 and so on, right?
Yeah.
And if you
Yeah.
have to do that, this, what is the divisors are these. We have to find the sum of these, right?
Yeah.
Sum of these is a geometric series. You know how to do sum of a geometric series, right?
Yeah.
I hope everyone knows that, how to do 1 plus 2 square plus 2 power alpha 1, suppose. The number of terms here is alpha 1 plus 1, right?
Yeah.
The formula is A into r power n minus 1 by r minus 1, where r is the common ratio.
Oh, yeah.
A is the first term, so first term is 1, and then r is 2. Number of terms is alpha 1 plus 1. So it becomes 2 power alpha 1 plus 1 minus 1 by 2 minus 1, which is what we are doing here, by the way. I hope it is clear what is happening here.
Yeah.
Yes.
So that gives us the sum of all the divisors. Okay. Now the third thing that I want to talk about is number of divisors of a perfect square. Number of divisors of a perfect square. Can you say something about it?
It's
A positive integer n is a perfect square.
it has an odd amount of values.
If and only if
It's a
d of n is odd.
yeah.
Right? Because perfect square has to have even powers in all the prime numbers, right?
Yeah.
So d of n will be some 2k plus 1. This is, let's say, alpha 1. And 2l plus 1. This is alpha 2, right?
Yeah.
Alpha 1, alpha 2 have to be even, all the alphas, right? For perfect square. So it is like a product of only odd numbers, right?
Yeah.
So this is the third point. The number n is a perfect square only if it has a dn comes out to be odd.
Yeah.
And the next point is complementary divisor. So we'll discuss what that means. So let n be a positive integer. Let n be a positive integer. If d is a divisor of n, if d is a divisor of n, then n can always be written as, then n can always be written as, n is equal to d times n by d, right?
Yes, yes.
So n by d is like a complementary divisor of d.
Oh, yeah.
Like no matter what divisor d you talk about, there is a complementary divisor n by d of it, right?
Yeah,
So divisors you can group in pairs like that, right?
yeah,
I hope you're understanding.
yes.
Okay. So theory wise, there is not much else to the theory. What we want to do is apply these 3, 4 things in problems and learn how we can do that. Okay. So
Okay.
now onwards, it will be questions practice. So I'll give you a couple of questions to start off with. 3 questions actually. So question 1 is n number is the product of two primes. Product of two primes. The sum of positive divisors of capital N that are less than n is 2014. Find n. Question 2 is how many positive integers less than 2015 have exactly 9 positive integer divisors. And question 3 is a natural number is called superb if it is a multiple, if it is a multiple of the number of its divisors. Okay, so you have to find the greatest superb 2-digit number, and B is prove that there are no superb numbers with last digit 3. So try these 3 questions. You have around 10-15 minutes to attempt it.
Hmm.
I'll be back in 5 minutes. Try it out. Okay. Is the first one done?
Yeah.
Yes.
Tell me what if anybody has gotten it.
4022.
Right. How? Tell me.
So if you let n equal p times q as the q prime,
Hmm.
then 1 plus p plus q is equal to 2014. And so p plus q is equal to 2013.
Hmm.
And if both p and q are odd, then
Hmm.
their sum will be even.
Hmm.
But since it's their sum to 2013, at least you know that
Hmm.
exactly one of them must be even,
Hmm.
and the only even prime is 2.
Hmm.
Then one is 2, one is 2011, and then the product is 4003.
Noah, you're getting it right.
Yeah, I did the same thing.
Okay. So the first one is easy only. Let's try second one. No, second and third. Any ideas for second one?
Well, I was thinking of just splitting it into cases.
Mm-hmm.
So, like, if you look at the case um, of just one number to the power of 8, like, I see
Mm-hmm.
that 2 to the power of 8 works, but 3 to the power of 8 is too big.
Mm.
And
So
then,
only one number, 2 to the power 8 or 256 is going to have 9 divisors. 256 is less than this.
Yeah.
yeah,
That is one case. The other case would be when there are multiple prime factors, right?
Yeah.
yeah,
Let's say there are two prime factors. What should be the powers?
2 and 2.
So it should be like this, right?
Yes.
So if there are three prime factors, can we do it? P, Q, R with some.
No.
We can't, because if it is 1, 1, 1, it will be 8, and if it is 1, 2, 1, it is too big,
Yeah.
right?
Yes.
yeah,
So no cases beyond that is possible. Only case left is this, right?
Yeah.
So for P square Q square, you should make it less than 2015 somehow. So PQ should be less than root of 2015, right?
Yeah.
The root of 2015 will be between 44 and 45, correct?
Yeah.
yes,
PQ should be less than or equal to 44, right?
Yeah.
yeah,
So now look at numbers less than 44, which are product of two primes, P into Q, something like that. Start from 2 into 3, it is simple only. You can get all the possibilities, right?
Mm.
yeah,
Then 3 into 5, 15. Then 3 into 7. Then 2 into 11. Then 2 into 13. 3 into 11. Then 2 into 17. 2 into 19. No, wait. 5 into 7 also. 2 into 19, 38, and 3 into 13, 39. After that, nothing is there. 40 can't be done. 41 is a prime. 42 can't be done. 43 and 44 don't work, right?
No.
So there are 12 numbers here, I think, and one number here. So the answer is 13. We need to keep PQ less than 44. Therefore, we don't need to check beyond it.
uh, yeah,
There is nothing else you can do here. You should just check the small cases, all the numbers which are like this. Correct?
Yeah.
yes,
Actual numbers that will come will be the squares of PQ, right?
Yeah.
So the real numbers that we talk about are 36, 100, 196, like that.
Yeah.
This is just to get the answer. The real numbers are P square, Q square.
Yes.
Is everyone understanding?
Yeah.
yeah,
Okay, so 13 is the answer for question 2. You can start question 3.
okay.
Part A of it, have you guys gotten anything?
Yeah, I got 96.
That's correct. Why is that correct? Because you should start from the highest two-digit numbers, right?
Yes.
Start from
Mm.
99. See that 99 is 3 square into 11 power 1. So the number of divisors of 99 is how much?
6.
Hmm. And 6 does not divide 99, right?
No.
Yeah,
98 and
that's not.
97 also won't work, but 96 will work. For example, 96 will be 16 into 6. So 2 power 5 into 3 power 1, right? So it is 6 into 2 number of divisors,
Yeah.
and 12 divides 96. So therefore it is a superb number. So we are starting from the highest possible two-digit number. So this is the largest one.
Yeah.
Yeah.
Okay. Part B.
I think I got part B.
Okay. What is the idea?
So pretty much, if a number ends in 3,
Hmm.
then in order to be a multiple of the sum of its divisors, it cannot be it has to be a square number. So if it's not a square number, then the sum of its divisors will be even.
Hmm.
No, the number of divisors will be even, and that will not work. So it has to be a square, but
Wait,
then
why does it have to be a square? Tell me.
because so any number that's not a square,
Hmm.
every divisor will have a complementary divisor, which means the number of divisors will be divisible by 2, and
Basically, non-perfect square will have even number of divisors.
yes, and even number can't divide a odd number.
Even number cannot divide a number that ends in 3.
Yeah,
And this number is ending in 3, it's odd.
yeah,
So therefore, for non-perfect squares, it doesn't work, right?
yes,
Yeah.
And now you have to check whether any number ending in 3 is a perfect square or not, right?
yeah, and it can't
Hmm.
with if you pretty much for any square number, the last digit will be determined by looking at the last digit of the number that you're squaring.
So it can be 1, it can be 4, it can be 9, it can be 6, it can be when you do 7, it is again 9. When you do 8, it is 4. When you do 9, it is 1. These are the ones, right?
Yeah, and 5. Those are,
5 also. And
and
0 also,
yeah,
but
but
nothing other than these.
yeah, no other than that, which means that
S- This is
it,
not a square number. And because it is not a square number, it has even number of divisors, and then it cannot be divisible by the number of divisors.
yeah,
Yeah.
Noah, are you understanding?
Yeah.
Okay. Question 4 is the sum of 3 different natural divisors of an odd natural number is 10,327. What is the smallest possible odd natural number is called n, by the way. What is the smallest possible value of n? Basically, we want to come to a conclusion where n is greater than equal to what, right?
It's
Smallest possible value of n. We need an
yeah.
inequality like this. We know that the sum of three different divisors of n is equal to this. So think about it. This is odd. That means 2 is not a divisor of n, right? No,
Yeah.
no. No,
This
that
is not
is,
Wait.
even one.
we can't say that, I think.
Like,
Oh, wait, it is odd number. It has been given. N is odd is given.
oh,
So we can say that. We cannot say that on the basis of this number. But we can
no.
say that because n is odd, right?
Yeah.
So 2 doesn't divide n. So let's try to think of the largest possible divisors of n, right? What is the largest divisor of n? N itself, right?
Yes.
Yeah.
What would be the second largest divisor of n?
And
Remember, 2 cannot divide n, right?
yeah, so n over
Yeah.
3.
So maybe 3 can divide n. But if 3 divides n, then n by 3 will be also divisor, right?
Yes.
So the largest possible divisor after n will be n by 3, no?
Yeah.
It may or may not be, but this is the largest possible value, right?
Yeah.
Similarly, 4 cannot divide n, but 5 could divide n, right?
Yeah.
So in that case, the largest divisor would be n by 5.
Mm.
See, these are the maximum possible divisors that you can get, right?
Yeah.
2 and 4 are not allowed, so n by 2, n by 4 are not allowed. So if I add these, n plus n by 3 plus n by 5, this is the largest possible value of the sum of three divisors, right?
Mm.
Sum of three different natural divisors. The largest possible value of it will be this, no?
But how do you know that that's the smallest for n?
No, these are the largest possible values of
Oh,
sum of divisors.
yes.
Correct?
Yeah.
I am not saying
Yeah.
anything about smallest. I'm just saying maximum possible value of three divisors can be this only, no? Nothing else.
Yeah.
So shouldn't this be greater than equal to 10,327?
Yes.
There should
Yes.
not be any
Yes.
doubt in this.
Yeah. It is.
Any other
Yeah.
three divisors would be smaller, no, than this.
Yeah.
And we have that sum of three divisors is 10,327. So this is the maximum value of it, right?
Yeah.
If you simplify this, it is 15 plus 5, 20 plus 3, 23 by 15 n, right?
Yeah.
Is greater than 10,327. So let's calculate n is greater than 10,327 into 15 by 23. So 23, 4s are 92, 11 and 5. Then you get 20. You get cancellation here. 4, 4 and 9, right?
Yeah.
Yeah.
Think about it. And 449 into 15 you have to do now. That will come out to be 5, 6, 7, 3, 5.
Mm.
Correct?
Yeah.
You can calculate it and see. You're getting n is greater than or equal to 6735.
Yeah.
Yeah.
And now check whether 6735 works or not, because equal to we should check. Check the number 6735. It is divisible by 3 and 5, right?
Yes.
So 6735 plus divided by 3 will be 2245, I think. Yeah. Plus divided by 5 will be 1200 and 735. 1347, right?
Yeah.
Add it up and see what is coming. 7, then 3 plus 4 plus 4, 12. So 2 comes, 1. Then 7 plus 2, 913. 3 comes, 1. And then 10 comes. This is adding up to this.
Okay. Oh, yeah.
Do you understand that it is adding up now?
Yes.
Yeah.
So what we have done here is we have looked at, okay, sum of 3 different natural divisors has to be this. So we thought of the biggest possible 3 divisors, right?
Yeah.
We know by complementary divisor method that these are the divisors that are possible, right? So we got an inequality, n plus n by 3 plus n by 5 is greater than this, and from there we got n is greater than 6735. And equality works. So the smallest value of n will be 6735, right?
Yeah.
Yeah.
Are you understanding? This is a nice trick.
Yeah.
Yeah.
Okay. What I will do is I will share some questions with you guys. We'll discuss some more questions and problems on this divisors concepts in the coming few classes. So
Okay.
by tonight, I will share the questions. You can look at it.
Okay.
Okay, fine. We'll do the class on Thursday or Friday sometime in the week.
Okay.
Okay, that's all for now then.
Okay. Thank you.
Bye.
Thank you.